All right, so we're going to talk about MPI, message passing interface. Okay, so believe it or not, there's a ship called the MPI Adventure, and it actually makes offshore wind power, windmill things.
Wait, the ship has windmills on it?
No, it goes out into the like the shallow ocean areas, and it's used to construct the big offshore wind projects.
Oh, okay, cool.
Yeah. Okay, so we're going to talk about MPI. We're going to kind of combine this with our parallel programming topics or concepts that we already learned. We're going to learn these 6 necessary MPI commands in order to write. You can write basically any program, maybe not efficiently, but any program with these 6 MPI commands. And then we're going to have an example program. Okay, so MPI, the message passing interface, is a standardized and portable message passing system that can be used on a variety of parallel computing architectures. So it's a standard. MPI is a standard. It has evolved over the years, started in the early 1990s, I believe. And the evolution of it is to accommodate advances in hardware and programming practices. So there's MPI standard documents. You can go read them. If tonight you're having trouble falling asleep, my guess, I'll put you out right away. So the earliest ones are much shorter, and then the latest one is much bigger. So MPI has been implemented by many vendors, and then there's also open source implementations available, of course. So Cray, now called HPE, they have their vendor implementation. Intel has a pretty good implementation of it as well. But then there are other ones like MPitch that came out of Argonne National Lab, and OpenMPI, another one. And those are both open source implementations. And basically what happens is you use the function library from MPI to write your C, C++, or Fortran program for your supercomputer. Okay?
We have a question.
Yeah.
So MPI is a standard and also a library.
Yes, the implementation is a library.
Okay, the
Yeah.
implementation is the library. Okay.
Yeah, that's right. Okay. So so like I said, early 1990s, 1994, MPI 1 was finalized and released. It really is kind of it was pretty basic, I guess, but it's really what most people use the most of. MPI 2 came out in 1996, and so there were some extensions. MPI 3 was in 2012. MPI 4 in June 2021, and MPI 5 in June 2025. So typically, if you're going to use an MPI library, it's probably going to be MPI 4 or earlier. MPI 5 just came out a year ago. It takes a while, often for the developers of the libraries to incorporate all of the features in the standard. So maybe there could be some MPI 5 libraries running around. I don't know. Maybe next year there will really be more. Okay. So I won't go into this too much, but the MPI 4 standard has some pretty cool features like partition communications in order to accommodate for GPUs and other devices. Persistent collectives. It adds some fault tolerance mechanisms, which is really nice because if you're running on 1,000 nodes and one of them fails, then oh, what happened? Most of the time your program crashes and you have to run it again. But with fault tolerance, there may be kind of a way around that. And then also some additional enhancements for hybrid programming. Okay, we're really not going to talk about MPI 4. Pretty much we're going to talk about things that that have been around since MPI 1. So I wanted to tell you about two programming paradigms. So these are the primary programming paradigms that we use when we are writing code for a parallel computer. So the first one is SPMD, and that stands for single program, multiple data. And then MPMD is multiple programs, multiple data. And we can use MPI for either paradigm. So I'm going to tell you a little more about how that works. So SPMD is you're writing a single program that will perform the same operation on multiple sets of data. So in the cooking analogy, this would be multiple chefs who are baking many lasagnas. Okay. Another thing is, like, if we were going to write a program to write a movie, like just like Shrek or something like that. I don't know. What is the cool movie out today that's
Toy Story.
Toy Story? All right, Toy Story, good. So if we were going to render different frames of our Toy Story movie, then that would be an SPMD operation, right? Because the different frames, there's different characters in them, they're doing different things. Okay. First, I think I just said the opposite of what I meant. The different frames, they have the same character in them. Well, okay, let me start that completely over. Sorry, I just got back from vacation. So we're rendering different frames of the movie because we have like different characters that are doing different things, but it's the same concept of how we render them, with whatever algorithms that we're using for rendering the characters. Okay. Okay. MPMD is where we're going to write different programs to perform different operations on multiple sets of data. So the cooking analogy is multiple chefs preparing a 4-course dinner. So one of them is preparing lasagna, because lasagna is a very fancy food, as we all know. One of them is preparing lasagna, one of them is preparing the salad, one of them is preparing tiramisu, I don't know, whatever. Okay. And then for our movie analogy, this would be if we're rendering different parts of the movie frame. So for example, one of them is rendering Woody and one of them is rendering, I don't know any of the other characters. One of them is Buzz. Yeah, Buzz. Right. One of them is rendering Buzz, one of them is rendering the background. I don't know. So that's the idea, is because they're doing different things. They're it's different algorithms, different programs effectively. Okay, so we can also write a hybrid program where we have some processes performing the same tasks and we have some that are performing different tasks. We can do whatever we want. Good. Any questions so far before we get to this? Any questions about what we're talking about? Yes, ma'am.
So SIMD is more on a hardware level and SPMD is.
Yeah, so SIMD is, that's a hardware term, yeah.
Okay.
Okay, good question, thank you. All right, so these are the 6 necessary MPI commands that you need to know, and then you'll be able to write just about any algorithm in parallel. Okay. Yeah, so let's go through what these are. So the first 2 are about initialization and termination of MPI. So MPI init initiates MPI. So you put this in the body of your code, like after your variable declarations, but right there before any other MPI commands. And it initializes the MPI environment. If you put it after other MPI functions, their behavior is undefined. So sometimes it'll work, sometimes it won't. Most of the time it won't. So what MPI init basically does is when you launch a parallel program, you are allocated a certain number of different nodes or processes. Okay. And what MPI init does is it gets everybody's ducks in a row and it straightens everything out and it figures out, how this is all going to work together. That's basically what it does. You could read the code if you wanted. Again, another good night reading if you're an insomniac. But that's basically what it's doing there. Okay. MPI finalize is its companion. That goes at the very end of your program. And it shuts down MPI. So init starts it up, finalize, shuts it down. Okay. And that's you can't, again, you can't put any other MPI commands after it, except if you wanted to call MPI init and MPI finalize again. I guess you could do it then. But otherwise, no other MPI commands. Okay. I know it sounds a little weird, so I'm going to keep going, and then hopefully it'll all become clear when you see an example. But do you have a question?
Yeah. Do we need to know anything when we call MPI init about what kind of resources we're asking for, or how many, or for how long, or anything like that?
We do not need to know anything about that. It's agnostic to that. Yeah, because that information about what resources we have and how long we have them for, that information is acquired elsewhere. And so ideally, the reason that we're going to use these and other ones that I'm going to explain here soon is so that our program can run on any size, independent of how many resources we have or how long we have. Great question, though. Thank you for asking. Okay, so these are, because you led me right to this, so perfect, thank you. So these are the two environmental inquiry functions that we need to understand. So one of them is called MPI com size. The other one is called MPI com rank. Okay, so MPI com size determines the size of the resources that you have. Okay, and it determines that from external data. Okay, so like when I run my code, I'm going to use something like srun, which I'm using Slurm, or I might use something called MPI run or MPI exec on other systems. And when you do that, you have specifications in with that command for how many MPI processes that you want to run. Okay, and so MPI com size is going to get that info from that external source runtime as you start running. Okay, so similarly, MPI com rank is going to tell each process what its rank is. Okay, so imagine that we are all working together on something. Okay, we are all processes. Okay, you just have to use your imagination. So MPI com size is going to count how many people are in this room, and it's going to return that number. Okay. MPI com rank is going to, so again, these are things that MPI init has already figured out. Okay, and then MPI com rank is just going to report back to you. MPI init decided, because Rebecca's the one standing up, she's process 0, and then you're 1, you're 2, you're 3, you're 4, you're 5, you're 6, you're 7, you're 8, you're 9, you're 10, you're 11, 12, 13, 14, right? 15. That's what it's going to figure out. This is great. We got 16 people in this room. Anyway, so the rank is going to be anywhere from 0, okay, we start counting at 0, to size -1, right? So we have 16 people here in this room. We are all MPI processes. I'm 0. All of you are a number between 0 and 15. Okay, does that make sense? Anybody have any questions about this? Because I know it's a little weird. Yeah.
So MPI com size, it returns the number of processors available and GPUs available.
It returns the number of MPI processes that are running.
Oh, MPI processes.
MPI processes, yes.
So, okay.
Mhm.
And then ranking them.
And then MPI com rank says,
In an order, basically.
yeah, the so again, MPI init has already decided all of these things for you, right? Like it figured them out based on the inputs from whatever else, I don't know what it is. Like I said, you could read the code and find out, but it has already figured that out. And then it tells like all different processes, this is you are rank 12 or whatever, right? Yeah.
When is it useful to know the size and rank of your processes?
When is it useful to know this? All the time. Okay, because what this will help you do is, okay, remember I was telling you about like the finite elements thing where we're dividing up our domain into little pieces, right? So if I want to distribute those pieces amongst all of the different processes that I have available, then I want to know how many processes there are, right? I want to know the size because it's great, we have 16 people in here. Let's say we have an 8x8 domain. Okay, so we have 64 little pieces that we want to divide up. So if we have 16 processes, we can just give everybody 4, right? Because 4 times 16 is 64. Yay, good math. Okay, if we had, on the other hand, if we had 8 processes, then we would give everybody 8 pieces, right? Does that make sense? So in this way, we can dynamically decide how we're going to distribute the work. Okay, and then knowing our rank, that can come in handy for other reasons. So typically when you write a code, if you have what they call a manager worker type of algorithm, then you have one process that is the manager process, and you have the rest of them that are the worker processes. And so it's kind of traditional to give process 0 the role of the manager, simply because you always have a process 0, right? Whereas you don't always have process 5 or something, if that was your favorite number. So that's one reason why you might want to know the rank. Another reason that you could want to know the rank is you could have kind of what we would call like an even odd sort of an algorithm, where even number of processes are doing one thing, odd number of processes are doing a different thing. And so then if you know, oh, I'm rank 5, I'm odd, then you know which part of the algorithm that you're supposed to be doing. Okay. And then finally, there are other algorithms where you might want to, so for example, if we're writing an MPMD sort of a code, we might want to, and this happens a lot like in climate simulations, like, well, I'm going to assign a certain number of processes to do the ocean part of the code. I'm going to assign another set to do the land part, and I'm going to assign other ones to do the atmosphere part, right? So that would be another way that you would be able to divide those up based on their ranks. Yeah. Okay, any questions? Cool. All right. So this is an example of kind of what it might look like on, so in this case, we have a cluster that has 4 nodes. And some of the nodes have the possibility of having 2 processes on them, and some of them have the possibility of having only 1 process on them. And so what MPI is going to do is it's going to take, okay, I want to have 6 processes here. And what it's going to do is it's going to choose where those go. So this is another thing that MPI init does, right? Is it decides, okay, I know I need to have 6 processes. These 2, why don't you go on node 1? This one can go on node 2. These 2 go on node 3, and that one go on node 4. Okay, that's something that MPI init would decide for you, and then that's what it would look like. So this is your it. We call it MPI COM world. This is kind of the global communicator between all of the processes that you have available for yourself. And so that maps it onto the reality of the cluster hardware. Okay. Now that's a little weird, but yeah.
Are the number of processes determined by the arguments that you pass into MPI?
The number of processes are determined by the arguments that you pass to srun or MPI run. But in our case, we're using something called srun because we're using Slurm. So you tell srun, I want to run on 6 processes. Yeah.
So here the processes are allocated to clusters based on the MPI standard. Like that's all handled on the back end. You don't have to-
Yeah, you don't have to worry about any of that. It's all handled for you by MPI. Yep.
If I get partway through this and I say, okay, well, node 2 has run out of work, and so I want to move process one onto node two. Is that a new MPI init, or can I, within existing setup of init and world and so on, ask it to reallocate things to balance the resources better?
No, you can't do anything about it. It's decided by MPI it decides. In conjunction with Flurm and what have you. Like, those are the things that decide it. You as a user can't do anything about it.
So it basically assumes all the jobs, all the individual processes are gonna have the same.
Yeah, so unfortunately, this diagram kind of freaks people out. But all this is just, this is some weird architecture where it happens that node two just has one CPU on it that can be used. Okay, it's not, I mean, like, it's just demonstrating that you can use this on a heterogeneous cluster. In our case, our cluster is, well, it is heterogeneous in the sense that, it has two different types of architecture on it. But within the one type of architecture, all the nodes are exactly the same. Okay, so on Perlmutter, this would never happen. On Perlmutter, you want 6 MPI processes, you would get 3 nodes or something.
I guess my question is more, when you write your code, you're assuming all these are gonna take about the same amount of time because I think I balanced the work well and I designed the algorithm.
Yes.
But then you discover that process 3 actually takes 5 times longer than the rest of the processes. And so you want to give it a whole thing and you put all the other ones on one.
Yeah. Okay, so what you're talking about then is something within my program. So if I was going to write my program, I would have to figure out how to do load balancing within my program. And so there are a lot of different ways to do load balancing, but there's things such as work stealing. So let's say I gave each of my processes 100 things to do, okay, just for the sake of argument. And let's say it turns out that process 3, like you're saying, had one thing that took 5 times longer than everybody else's things, right? So by the end, 0, 1, 2, 4, and 5 are just sitting around, twiddling their thumbs with nothing to do. So if I have it built into my algorithm, then I could do work stealing, where node 3 still has, 5 things left in its queue. Everybody else takes 1, and then we're done quickly. So yeah, you could do that.
And I guess just here specifically, is that you MPI finalize, you reallocate everything, then you re-MPI init? Or is it within the
No.
setup of MPI, you can move things around?
So you can move your tasks around as long as your program allows it to do that. So you would have to build in that kind of logic into your code. Yeah.
You are mapping a one-to-one there. Do MPI share cluster resources between 2 processes?
Yeah, yes. I mean, I didn't make this. Okay, but in this case, we're assuming that each CPU gets 1 MPI process. And so node 1 has 2 CPUs, node 2 just has 1 CPU.
No, but I mean, the CPU can be shared by 2 different processes.
It could be. It could be, yeah, if you allow that. Yeah. But in this case, we're not. Yeah.
Yeah, I just want to make a comment that process to CPU and GPU schedule mapping is done by the scheduler. The operating system scheduler and the user is not involved in scheduling.
That is correct. That's correct.
So if there is a need to move process 1 from first node to the second node, then it's done by the scheduler.
Yes, right. It would have to be done by the scheduler or something. And that's like something that I think in MPI 4 they can kind of do, like with the what was it? Sorry, my brain. Well, like where it said they were they have more protection against, gosh, come on, we'll cheat and go back here. Yeah, fault tolerance, that's what I was looking for. So with fault tolerance, they may be able to move processes from one node to another. I don't actually know how they do fault tolerance. Yeah, somebody else have a question? Yeah.
if I'm correct, the job allocation, the node allocation and all that is not MPI, but Slurm.
Yes.
MPI
scheduling.
coming.
Correct.
Yes.
Correct.
scheduling, yes.
So Slurm, so, okay, when you submit your job, what happens is it goes to Slurm. And Slurm says, okay, yeah, I can run this. It's gonna be running on these nodes. Okay, and then those are the nodes that you have, that you're allocated for a particular amount of time based on what you requested in your job script. Yeah, and then once you get there, then srun says, okay, I have these nodes. I want to run this many ranks. Here's the rank number for each one, right? Okay, any more questions or we'll go on to the. Okay, good. So the next thing is about message passing. So I mean, it's the message passing interface. We haven't learned anything about passing messages. So first thing is there's MPI send, okay? And this is a function that sends data from one MPI process to another. So in this particular case, okay, so first I should say these are the C prototypes of these functions. I like C. And you can use them in C++, or they have a different prototype in Fortran, but I didn't want to confuse you all with Fortran, because probably none of you know Fortran. Anybody here know Fortran? Okay, yes, you do. You have to be of a certain vintage to know Fortran. Okay, so we're going to send a message. So we put the message in this thing that's called buff in here, okay? And the reason there's that little star thingy there is that means the address of buff. So what we're sending, what we're providing to MPI send is the address of a location of memory, okay, that contains the information that we're gonna send, okay? Now count is how many pieces of information that we're sending. MPI data type is what type of data that we're sending. So a double, a float, int, whatever. The next one is dest, that's the destination. So that's the rank of the process that we are going to send this information to. Okay. And then tag is just kind of like, it's a tag. It makes, like maybe I'm going to send multiple pieces of information to you, and I want you to be sure to know which one matches up with what you need. So I would put a unique tag on that. And then the last thing is the communicator. And the communicator is, well, the communicator, as was in here, the kind of like the world in which we live and we are sending information within it, okay? Because you can actually, just to make your lives more miserable, you can actually make other communicators. You can make like a sub-communicator where it's like only the even numbered processes or only the odd numbered processes or whatever you want. You could make a sub-communicator. We're not going to really talk about that today. Okay, so let's talk about this. So my example here is MPI underscore send, and then I have ampersand x, okay? In this case, what I have is I have a variable that I defined somewhere, and it's a double, so I define like double x, semicolon, right? Like at the top of my program. And then I want to send it, and because, again, I need the address of the location where this information is that I'm wanting to send. That's why I have that ampersand for x, okay? And then 1, because it's just a length 1, right? It's not an array, it's just 1. And then MPI double, because I'm sending a double. I'm sending it to my manager, because, send it to a manager. I use my rank, I'm saying me is my rank, okay, as the tag. And then MPI underscore com underscore world, that is a macro, I guess, that is defined by MPI. And so then it'll understand that that is the communicator that you're using. Okay. I'm going to talk about receive, and then we can talk about both of these together because you have a send, you need to have a corresponding receive. So what this does is it performs a blocking receive of data from other processes. So again, it looks very similar to send. So we have this buffer where we're going to receive the information into. We have count, which is how many pieces we have. We have the data type, which is the particular type of data that we're using. The source, which is who sent this to me. And then the tag, which is, again, a unique identifier that we can put in there to make sure that this message matches correctly with the sends and receives. We've got the communicator again. And that's like, within what kind of universe are we sending this information? And then the status. So that's a new one. That's unique to receive. We don't have that. We don't have status in send, as you can see. So in my example here, again, I'm receiving this information. I'm like trying to receive from that previous set, okay? So I'm receiving it into X here, which again was just defined as double X. And so I need the address of that. So that's what the ampersand is. I'm going to send one piece of double, and I'm getting and receiving it from the source. And I know that it used its own rank as the special tag, and we're in the MPI com world, and we're getting the status. This will return a value actually. And so, anyway, so I was telling you about the receive function I said before. It's blocking. Oh, but wait, I was gonna see if anybody had any questions. If that blew your mind too much, or if you have any questions. You're too baffled, or you understood everything. I'm gonna go with you understood everything. Okay, so the receive function is blocking. So what this means is receive is gonna just sit there forever until it gets the message. MPI send may or may not block. It depends, kind of implementation dependency. So because of this, we had to watch out for deadlock. This is like the number one problem that first time MPI programmers and actually veteran MPI programmers run into, is that you'll have some kind of a blocking function that you didn't quite realize, that maybe you didn't have everything in quite the right order, so you have to debug it. So with send, it may or may not block, but typically if you're sending like a big message, then it's going to block. It's kind of like if, let's say you order like a USB cable from Amazon, they're just going to leave it on your porch and be done with it, right? If you order like a $10,000 computer from Amazon, they're not just going to leave it on your porch, right? They're going to call you, or they're going to make you sign for it or something. Make sure that you get it. And if you're not there, they won't leave it on your porch, right? So this is a similar deal. If I'm sending a small message, if you don't get it, I'll just send it again, no biggie, right? If I'm sending you a big message, then I'm going to make sure that you're there. So what often it'll do is the send will be like, hey, are you ready to receive? And if it doesn't get an answer back that, oh no, I'm not, or that I'm ready to receive, then it'll keep asking, are you ready to receive? Until finally you're ready to receive, and then it'll send it, right? But it's a pretty big investment to send that thing out, right? Okay, so if you have send and receive operations that are not properly ordered, you will have deadlock. And to avoid them, we want to make sure that our send and receive operations are properly matched. There are other non-blocking communication functions that you could use if you want to. But basically, we want to make sure to avoid any kind of circular dependencies. So here's my example of a program that will always deadlock, okay? The purpose of this program is to demonstrate deadlock. But in this case, what we do is we have an even number of MPI processes, okay? And we're going to have nearest neighbors send their rank to each other. Okay, so like I'm process 0, you're process 1, we're gonna exchange. I'm gonna send you 0, you're gonna send me 1, right? Like that's my goal here in this code. Okay, so here's how my code works. So first of all, I initialize all my variables, then I do MPI init, okay? And then I calculate, or I'm sorry, I put the size and the rank there because I want to get the size of our of our communication world, and I want to get my rank within that world. Okay. So if we don't have an even number, we're going to quit, because we need to have an even number of processes here. If I am an odd number process, then I'm gonna send to my neighbor who's below me in rank, just below me, right? If I am an even number, that's what the else is, then I'm gonna send to my neighbor that is 1 rank above me, right? So if I'm 0, I'm sending to 1. If I'm 1, I'm sending to 0. If I'm 5, I'm sending to 4. If I'm 6, I'm sending to 7. Make sense? Okay. So now here we go. I'm gonna send my data. And then after that, I'm gonna receive data from my buddy. Oh, I'm sorry, I did it backwards. I'm gonna receive data from my buddy. Just got back from vacation, pardon me. I'm gonna receive data from my buddy, and then I'm gonna send to them after I receive their data, right? How's this gonna work? And then after that, I'm gonna print out, hey, I sent myself to that processor and I received this from them. Yay! I'm gonna MPI finalize and I'm gonna return 0. Okay, how's this gonna work, folks? Any thoughts? Is this a brilliant plan? Yeah.
How, I guess, will it get on deadlock at the receive line because nothing has been sent yet?
Exactly, it's gonna get deadlocked at the receive line. So think about it. Let's say you and I are in this together, okay? So we're both kind of marching down these instructions at the same time, basically. So we both get to this point where we're gonna receive. So we both have our hands out like this, right? And then nobody is putting anything into our hands because that's the problem, is that we're both waiting to receive. Receive always blocks until it receives something. So this code is just going to hang either until the end of your allocated time from Slurm, okay? Or when the computer fails, or when the computer gets decommissioned, whichever one comes first, okay? Okay, here's another example. So then we just switch them around. This is basically the exact same thing. It's just that first we send and then we receive, okay? This will probably work because again, we're just sending like a USB cable or something. We're not sending a $10,000 machine, right? Because we're just sending 1 integer. So if I send you an integer and it didn't make it, I'll just send it to you again, no biggie, right? So this will probably work in this particular case. But if we were going to send something, a bigger payload than an integer, than a single integer, like if we were going to send, I don't know, it depends. There's kind of a, do you know maybe, Marcella? There's like a cutoff for the rendezvous versus the, you don't know. It's in the code for the HPE machine. You can look it up. If you do man MPI, you'll probably find it. But there's kind of a cutoff point where below a certain number of bytes or kilobytes or whatever, it will just send it. Then there's above that, then it does what's called rendezvous. And again, that's where it makes sure that you're there, you're ready to receive the data, okay? So with 1 integer, it's definitely just gonna send it to you. But above a certain threshold, it's a pretty big threshold, but I don't remember what it is. It will hang. So because we're both sending and we're both like, hey, have you received this? Are you ready? Are you ready to receive? Are you ready? Right, again, we're gonna have the same problem. If it's put to the rendezvous, we're gonna have the same problem where It's gonna keep going until until Slurm cuts you off, until the machine goes down, or the machine gets decommissioned.
So
Yeah.
here the deadlocking would occur because MPI is sending and also MPI receive is sending as well, both to CommWorld.
Because everyone is sending at the same time. So let's say you and I are partners, right?
Yeah.
So if we're going down this program in order, then I'm like, hey, here you go. Are you ready to receive?
Yeah.
And you're also doing the same thing. You're going, hey, are you ready to receive? Neither of us are actually ready to receive.
Could you point to the line where the two processes are sending?
Right here, MPI send.
Okay, so and what's being sent is the two processes are MPI.
So we're sending me, which is
Okay.
whatever our rank is. So
Okay.
let's say my rank's 0, your rank is 1. You're trying to send me a
Those are
1.
the two processes.
Yeah.
That to the send.
Yeah, and so I'm trying to send you a 0.
Yeah.
You're trying to send me a 1. Okay.
Okay.
Now, in this case, probably like if you could think of it as a baseball or something, right? I can probably throw a baseball at you. You can throw a baseball at me at the same time, and we can both catch with our catcher mitt, right? But if you were giving me a giant, I don't know, like a whole pallet full of baseballs, right? Then you can't throw that at me while I throw my giant pallet full of baseballs at you, right? So we would have to exchange. You'd have to have like your forklift ready to receive my pallet, right?
Okay.
And vice versa. Okay, so here's how we can totally fix this problem. So again, this is the exact same program. The only difference is that if I am an even numbered process, then I'm going to send first and then receive. But if I'm an odd numbered process, then I'm going to receive first and then send. Okay, so let's say I'm process 0, you're process 1, right? So I'm going to send you my data. You're going to be there ready to receive it. Okay. And then after my data gets sent, then I'm going to start receiving, and you're going to be ready to send me your data. Okay. And this is a safe example. This will always work no matter what. Okay. Anybody have any questions? Yeah.
In Linux, we have a file called pipe type that we can send and forget about, and anybody can read at any time. We don't have this solution in MPI.
We do, but not in this particular function.
Okay.
So there are a number of things. So first of all, we could do I send or I receive, and what's the I stand for? I don't remember the word, but that is asynchronous. Okay. Then there's also as of MPI 3, there's also one where you don't have to have a send or receive. It'll just send it off and write it to it. I forget what that one's called too.
Okay.
But yeah, that does exist. I think, when they were writing this back in 1996 or whatever, 1994, I mean, it was hard enough to do just this type of coordinated send and receive. Okay, any other questions? Okay, we already went through these explanations, but I just have them here for posterity's purposes. So if you want to come back and look at the slides again, you can see why this is. Okay, so we're going to take a break now. Come back, everybody. So we're going to do a little exercise about how to compute pi in parallel. Yay. Okay, in case you couldn't tell, I love math. I don't know if you noticed my shirt. Today's shirt is polar functions. Yeah. Yeah. A lot of sines and cosine. There's no pi actually on this shirt. I thought there was this morning. Otherwise, I would have picked a different thing to wear. But anyway, I love pi. So we're going to compute pi in parallel simply because it's easy to understand, but in real life, you don't want to actually compute pi this way. So we're going to talk about it. So project, we're going to show you the serial code. I'm going to have some parallelization strategies, and then the assignment, but we'll just walk through the whole thing together. Okay, so we want to compute pi. There's a method called the method of darts, which is actually a really terrible way to compute pi. So don't actually do it in real life, okay? But in any case, it's an easy method to understand. That's why we're going to use it. But the concept behind this is that the ratio of the area of a square to the area of a circle that's inscribed inside of that square is proportional to pi. Okay, so here we go. Let's say we have a dartboard, radius r, inscribed inside of a square. Okay, so the area of the circle is pi r squared, right? Everybody knows that. The area of the square, so the radius is r, so the side is the same as the diameter of the circle is 2r. So 2r quantity squared, so that's 4r squared. So then if we just take the ratio of those, then the area of the circle over the area of the square, pi r squared over 4r squared, r squared canceled out, and we get pi over 4. Okay? Everybody see that? Make sense? Great. So, okay, this is how we can do this. But then, like, how do we actually like find those areas? Like, how do we do that? Well, let's say that we actually had an actual dartboard and we threw darts completely randomly at that whole square area. Okay, we could just count the number of darts that land inside of the circle, and the total number of darts that we threw that landed inside of the square somewhere. And the ratio of those numbers would give us an approximation to the ratio of the areas. And the quality of our approximation increases with the number of darts thrown. But keep in mind that we actually have to throw 100 times more darts in order to get an additional significant figure. So this is a really bad method to compute pi. Okay, but it's easy to understand, so that's why we're working with it. Okay. So pi is going to be 4 times the number of darts inside of the circle divided by the total number of darts that we threw. Now, I love pi. Well, I love pi day. I love the number pi. I'm not a big fan of actual pies necessarily, although some of them are pretty good. But in my youth, I made a pi method of darts cake. And so I had a square cake and I had a circular cake, and they have the same diameter. And so then I just put one on top of the other and I sprinkled it with sprinkles. However, I don't think if you count the sprinkles that you're going to get the right ratio, unfortunately. So,
Did you calculate the ratio?
you know, I should have, but I didn't. Yeah. I think my circle is actually a little bit bigger, and also it's kind of it's not like flat, so it wasn't perfect. And I definitely need to make a new one someday so that I can get a higher resolution picture. Yeah.
Just out of curiosity, like, how did you make sure that they didn't go off to the side, outside of the square, I guess?
Oh, well, if they were to go outside of the square, you just ignore them.
There we go.
Yeah. Okay, so now we know how to do it in real life, right? But we don't know how to do it on a computer. Well, it's not that. So first of all, we just decide on a length, r. Okay, I like 1. 1 is always good. And then we generate pairs of random numbers x and y, such that x and y are between -r and r. And if x, y lies within the circle, meaning x squared plus y squared is less than or equal to r squared, then we add 1 to our tally for inside the circle. Otherwise, we don't. And then we find the ratio of the total number that were inside of the circle and the total number that we threw. Okay. Any questions about this method? And we have any questions about how this would work exactly? I mean, we'll get into more details, obviously. Oh.
Well, just look at,
Okay.
slides are fine.
Actually, I think this is a little bit, right?
I think it's working now.
Oh. Oh.
We're gonna get the,
Oh, I'm there. Okay. Well, that's nice that people wanted to see me. I think they wanted to see my shirt. A little bit. You can see the polar button on my shirt. Okay, so our code is actually a little different than this, right? Because we updated it yesterday.
Yeah.
And we didn't,
This is new.
but we didn't update the
Oh, I
slide.
forgot slide.
That's okay, we'll fix
Go to
it.
the Git repo to see.
Yeah, we'll do the get repo.
Right, I should.
So this, actually, this part is gonna be basically.
This is not changed. This is also changed because I'm calling the thread safe random number. The
Okay,
function is a call. Yeah,
it'll be slightly different than this, but it's almost the same as this.
yeah. Can find updated slides in the codes in the GitHub repo.
Yeah, and then our number generator is different than this too, because we just changed it yesterday, sorry. And so there's also Fortran version, if you want to use Fortran, if you like Fortran. Anyway, so the code is gonna look different than this slightly, but it's gonna be basically the same code. Okay, so let's talk about parallelization. So let's talk about what tasks are independent of each other and what tasks have to be performed sequentially, and then we'll use pecan to design our parallel algorithm. Okay, so first of all, what are the tasks? Maybe we'll just go with this. So if we're going to partition, we're going to decompose our problem into the finest grained tasks to maximize the potential for parallelism. So I would say the finest grained task is the throw of one dart, right? And each throw is independent of all others. Right? Like if we were doing this experiment in real life, if I'm throwing some darts and you're throwing some darts, it doesn't matter like what order that we throw them in, right? Doesn't matter. Yeah.
In this case, since we have to pick an X and a Y, aren't each of those independent tasks? You could.
Yeah, ideally they would be, but they're not. Yeah, because we have to use a random number generator in order to generate. So, I can tell you more about that, but I don't want to bore everyone. But it's actually one of my favorite topics to talk about. So I will tell you about that separately. So the point though is that those are separate tasks, right? That it doesn't matter if I throw the first dart or if you throw the first dart. Like if we were going to throw 1,000,000 darts and we had 1,000,000 people throwing darts, it'd be weird, but cool. It wouldn't matter if I threw the dart first and then you threw it, or if some random person threw it first and then you threw last, like it wouldn't matter, right? We would still get the same answer. And so if we were gonna really break this down into the finest grained tasks, if we had a huge computer, huge supercomputer, we could assign one throw to each process. We could have 1,000,000 processes. Unfortunately, I forgot to reserve a machine that big for us today, but I'm just kidding. We could do that in theory, okay? So next is communication. Okay, so let's think about communication. So each processor is going to throw a dart and then send the results back to a management process, right? Because somehow we need to tally it up, right? We have to have somebody keeping a record. So if we had 1,000,000 people, and let's say I'm the manager process, then I would have to keep a tally, and I'd have like a pen and paper here, and people would come up to me and they'd say, yes or no, right? I'd tally it in. So you can see this is a very very normal type of an algorithm where you have a manager worker sort of a paradigm, where you have a manager who sort of coordinates everything and you have workers that do all the work. Yeah. Just like real life. Just ask Helen. Bad manager joke there. Okay, so then let's think about agglomeration, where we're going to combine into coarser grained tasks to reduce the communication requirements or other costs. So in order to get a good value of pi, we have to use millions of darts. So you remember I told you, if we want to get another significant figure, we have to do 100 times more throws. So yeah, we're going to have to use millions of darts. We don't have millions of processors available. Forgot to reserve that for us. I'm just kidding. But even if we did, the communication costs would be huge, right? Can you imagine? Like 1,000,000 processes, they're either going to return a 0 or a 1, depending on whether their dart hit inside or outside of the square. And then we have to add all of those up, right? And the time that it takes to compute the dart throw is insignificant compared to the time that it takes for the communication to occur. All right, if you think about it, we're talking about effectively the speed of light. So within a processor, we're at nanoscale. In the communications, we're at several feet or something, right? At least for the communication traveling through the wires. So it's going to take a lot longer to communicate than it is to compute. So instead of having millions of processes, maybe we could just divide up the number of dart throws evenly between processes so that each one does a share of the work. So if we're going to do 1 million dart throws, we could even do 2 processes and each of them does 500,000, or we could do, anything like that. Maybe we could have 1,000 and each of them does 1,000. We could do it that way. Okay. And then the last thing is mapping. So we're going to assign our tasks to processors subject to the trade-off between communication costs and concurrency. So we're going to assign the role of manager to processor 0, right? Because that's just the standard way that we do things, because you always have a 0, but you might not always have a 5 or whatever your favorite number is. And so 0 will receive tallies from everyone else, and it'll compute the final value of pi. And every processor, including the manager, will perform an equal share of dart throws. Okay, sound good? Anybody have any questions? Anything up to this? No, it all makes perfect sense. Yay! Okay. So here's what we're going to do. We're going to clone the whole thing, parameter, from our repository using git clone blah blah blah. We're going to copy. Is it all, Helen, is there a .h file now?
Yeah, Fortran also has a .h file.
Okay, there's still a .h file. It's not called LC generator. We're going to copy that and we're going to parallelize the code using the 6 basic MPI commands. We're going to rename our code starts-mpi.c or .f90, depending on whether we're going to use C or F90 Fortran. Okay? Any questions here? That makes sense. All right, so what I'm going to do is I'm going to do hands-on here. So I'm going to do this too. Okay, so first I'm going to do SSH proxy because I haven't logged into Perlmutter yet. So I like to use SSH proxy. I don't know if you've ever heard of SSH proxy. Yay, I authenticated. Boom. So now I am able to SSH to Perlmutter without having to enter my password. SSH Perlmutter.nurse.gov. Okay, here we go. All right. Okay, so I'm going to CD to my Scratch directly. Okay. Here are all my exciting things that I have here. Okay, I suspect that my Scratch that got emptied out. Okay, so let me just remove that. So I've done this a million times, right? So I had the old one, the old version there. So I'm going to get the new version. And so I'm going to use this command, git clone, blah, blah, blah. Copy that here. Oh, it's trying to stop me from pasting. It thinks it might be from a scammer. That was interesting. Okay, so I'm cloning this in. Okay, so now let's look. CD crash. Of course. Let's starts. Let's see. Let's wait. See.
Go to Dart.
Hmm?
Oh, yeah, just do it. Okay, yeah.
Is this still okay? It's all right.
You good?
You.
Okay, so let me just look
Yes,
at,
Alec.
My Dart suite has significantly fewer files.
Yes.
I think if you go into this folder, there'll be.
Oh, is that
here's the, oh,
This is the code, which code is this? Dart.c?
darts.c.
Serial code.
Oh, my screen, sorry, folks. Okay. That's my code, and then, if I can cat, Oh, Fred safe version, okay, great. Okay, so I'm gonna copy both of these codes. Copy, arts with,
Why do you have to copy them?
why do I have to copy them?
We already cloned them, right?
Yeah, I'm just copying them elsewhere, so that I can.
Change them.
Yeah, because like otherwise I'm gonna overwrite because I have all the answers in there too, right? So I don't wanna overwrite my answers, I just wanna write a fresh. Darts, C and darts, read, C, start photo, LC generator, age. Copy them to my scratch. Okay, so if I look here, you see I've got darts.c and I've got LC generator.h. So now I'm gonna edit darts.c.
Is that CP copy?
Oh, yeah, sure, sorry.
Darts.c, Dart suite. Oh, I have inside already.
So you want to move that to the Oracle directory?
Yeah, that's what I did. You can move it somewhere else if you want.
Dart. Dart. C. And LC generated.
Yeah, we need both of those.
Okay. Yeah. Oh. BWD.
Yeah,
What was the git clone link again?
it is in the Q&A doc. Yeah. Maybe towards the top of that. Could be if you. Right here, yeah. CD scratch so that you can be in your scratch directories and then git clone the thingy. Yeah. Okay.
Or do you copy them?
I just copied them into my scratch just the base scratch directory of my own. You can copy them wherever you want. I just wanted to get them out of that particular directory.
Okay.
So that's why I copied them into my scratch directory sort of thing. Okay. So I'm gonna edit it now. I use the VI editor. Others may like to use other things, but you're of a certain vintage, you like the things that you like, and this is what I like. So the VI editor has two modes. One of them is command mode and one of them is input mode. And so right now I'm in command mode. And so I can move around, I can do various things. But then when I want to do input mode, then I just go I, and that'll put me into input mode and start me at the location where I am. Okay. So let's see. First thing we need to do for our code, right, is we need to add the MPI headers files. So the way things work in C, I don't know if anybody else is terribly familiar with C, but the way things work in C or C++ is you have these header files that have sort of basically like, I forget what it's called now, but they have like a kind of a the description of how the function is formulated. So there's one called MPI.h, and it has all of like the anyway, it has function prototypes, I think is what they're called, of the various MPI functions, including MPI init, MPI finalize, MPI, all of those things. And it also has prototypes for like the different data types that are in MPI. So you could read that file, like I said, be a great way to fall asleep at night if you wanted to look at that. But it kind of provides an overview of all of the functions. So when you do this pound include thing, what that basically does, it basically means that when the compiler is going to come and look at this thing and try to compile it, it's going to input these header files, these that have these function prototypes, so that when you get down into your, down in here and we have those functions, it won't be surprised. Because the C compiler doesn't like to be surprised. So if you don't have that there, then it'll be like, what's MPI in it? I've never heard of it. And then it'll barf because it'll be unhappy with you. Okay? Make sense? Okay, so where would we put our MPI in it?
For the for loop.
Before the for loop, that's right. So we would put it after our variable declarations, but before any of the action happens, right? Okay. So I'm going to put it here. Okay. Init. Ampersand RC. RV. Boom. Okay. So we've initialized MPI. What other things are we going to probably do? Oh, well, let's put in our MPI finalize next. Okay. Another thing is I'm super paranoid, so I'm going to write my file. I'm always saving my file. Okay. So we would put our MPI finalize here, just before the return 0. Okay. MPI finalize.
If you put MPI finalize before, like at a certain point, we don't care about what the rest of the processes are doing, and we just want to like print like all this print stuff. Like we don't want to do that on every rank. So if we put MPI finalize at a certain point, will that like only execute the following commands on the main rank?
I don't actually know. But the problem there might be, it would be undefined. So anything that you do basically after MPI finalize that has anything to do with your parallel processes is undefined.
Once you've accumulated on like the master rank and you
Hopefully that would work. We can try it both ways and we'll see.
Okay.
Because I don't know actually, because I know that like before, in general, what happens is like usually, typically, but again, this is implementation specific. Typically, before the MPI init, I would assume after MPI finalized, it would be the same way. It would just do however many copies of the code. It would just execute the same thing. Like let's say we had 4 MPI processes, because again, SRun knows this is where you would tell it.
It would do like 4 serial
It
processes.
would do like 4 serial processes, exactly, and it would do the same thing. So you might get one of them that would have the correct number, but then you'd have three more that didn't. So it's probably best to keep it inside of the MPI finalize and just make it so that only the manager process does that part. That makes sense. Okay. Yeah. So that's just pretty standard for MPI. So like if we go back to these codes, yeah. Oh, no, not that code. Wrong code. These codes. It's just MPI init is just this RC business. I don't know why. That's just what it is.
But in the main, like, we're not defining RC and RV in the main in
No, those are
dart stud.
predefined with C.
Well,
So
you define them in the function signature, but in our main, they're not defined in the function signature.
oh, yeah,
Well,
well,
that through an error.
everyone matters. So argc is the number of arguments and RV is the arguments to the code.
But I know, but like in R,
Mhm.
there's been a long time since I've programmed in C. But like if you scroll like,
Yeah, if I scroll up here, it doesn't have it. Yeah, it doesn't.
yeah, it doesn't matter. Like it'll know what those variable names are regardless.
Yeah. Yes.
You already said this, but why don't we need to include the MPI package? Is it already in standard IO library or?
So we included it right here. Yeah.
It's not in the deadlocking example.
Oh, shame on me then. Oh, no, it is. It's just, it's the first one. I just swapped the order. No, it's okay. I just swapped the order there. Okay, great questions. Everybody's asking good questions. Okay, so we're probably gonna do some MPI sends, right? This is our, so we're gonna need an MPI status, I would say, as a variable. Let's add some variables. MPI status. I can spell the word status. Status. I can spell status. There we go. So we're gonna need our status. We're gonna need a few other things, right? We're going to need some special variables to hold our final variables and yeah, we're gonna need a few things here. We're gonna need our rank, right? So that is integer rank. We're gonna need size. We need those. What else are we gonna need? Oh. Oh, I know what else we're gonna need. We're gonna need my files. Okay, so let's start with these variables. We'll probably need more. Okay, so we did MPI init, then we're gonna do, let's see, MPI rank. So let me look at this. Yeah, okay.
Communication size, we don't need a communication size before the icon size.
Oh, yeah, we'll need that one too. We'll get there. I'll just put that, yeah, and the other one I didn't put it first, so size. Okay, so we're gonna need the size and we're gonna need our rank in the size, right? Because the main thing is we want to figure out with the rank, we want to figure out, am I the manager or not, right? If I'm the manager, then I need to be able to collect all these things. If I'm not the manager, then I need to send it to the manager, right? And in fact, if we're gonna be really good at this, we need to, go ahead and add another variable here, int manager equals 0, because that's better than actually comparing to 0. Okay, so, how do I figure out how many trials that I get? Divide, okay, right.
By the sites.
Hmm,
Divide the number of trials by the sites.
by the size, yeah, that's right, okay. Question for everyone, is that always going to work?
Not if it's not an integer.
Hmm?
Should we floor?
We don't have to worry about that because, C will automatically floor, yeah. But what else?
If it's not an integer, then like it's not even divisible,
Any
like we
remainder.
divide by the wrong number.
Right, we may have a remainder, right, so let's say, I mean, let's just do a simple case. We're gonna throw 10 darts and we have 3 processes, right? And 10 divided by 3 is gonna give 3. So then each of our 3 processes is gonna do 3. 3 times 3 is 9, so we're missing 1. So how do we get that back?
Manager not do the rest.
So cost,
We could make the manager do the rest, but manager has other things to do. So maybe we should give it to everyone else except the manager.
so we,
Then whatever remaining numbers are, you can allocate to the other processes.
Yeah, so how do I decide who to give those to and how much to give them?
yeah. We do,
Just like loop through the processes that aren't 0.
One to one of them to each individual. Let's say there is one remaining, right? So just give it to the first one.
You could give it, yeah, you could do that. And then what if there's 2 remaining?
Then give like 1 and 2.
Okay,
And the remainder will always be less than the total number of processes. So we can always fit with like only additional 1 task to each one of them.
yeah, okay.
Could there be a way to,
So go ahead.
could there be a way to figure out whichever process returns first, like, or finishes its task?
Yes, if we were writing a more advanced program, we could do it that way. But because this is a pretty simplistic program, by the time it took you to figure out who was free, it would take longer than just doing the task. So, that's what you might call like a work stealing sort of a paradigm. But in this case, it would be too hard to implement it compared to what we're doing here. But that was a really good idea.
I have a sort of lazy approach, which is that particularly for large numbers of total trials, if we just give 1 extra trial to each process, then you're not ever short and you get a slightly more accurate. I mean, it depends whether we really care about getting exactly that many trials.
Yeah, well, but then we're not gonna get the exact same number of trials, but yeah.
If we know the remainder,
Uh-huh.
then we can loop through all of the non-manager processes and just incrementally add 1 to each
Yes,
until we reach the end.
okay. The thing is, though, everybody's doing this on their own. Everybody is figuring this out independently, how many I have to do. So we can't really have a loop like that. But your idea is correct, like that we can just give out 1 to every. Yeah. Okay, yes,
What would be the loop stopping condition? You just do that individually in each process.
correct. We just do it because we just want to calculate it locally because we could have a thing where there was some central process that like figures it all out and sends out the information. We could do that. But in this case, this information is so easy to just calculate ourselves, so we'll just calculate it ourselves. Okay, so my num trials is going to be equal to the num trials divided by the size, right? Plus 1 maybe for some people. Okay, but for everyone, it's going to be that. And then I liked your idea, I think it was your idea, where you say if your rank is equal to, let me think if this is gonna work. If you're not process 0, okay, so if you're not the manager, and if your rank is less than or equal to the remainder, then you gotta add 1 on, right? Because the maximum, so if we have 7 processors, let's say, just to be the most inconvenient number possible, 7, then at most, we're gonna have a remainder of 6, right? So if we had a remainder of 6, then everybody who was 1 through 6 is gonna take 1 more on, right? If we had a remainder of 2, let's say, we had 7 processors, then only 1 and 2 are gonna take on extra work. And 0 is left out of the equation because we don't want 0 doing anything else because they're the manager already. But then just 1 and 2, and then 3, 4, 5, and 6 are gonna have just the standard amount of work. But 1 and 2 are gonna have extra work. So let's figure out how we can express that mathematically here. So, let's see, if num trials mod is this percent sign. Mod size is less than or equal to the rank. Okay. And, okay, let's do this. This is gonna have to be like a double loop, I think, or a double thing. Condition. And rank is not equal to manager. And then we are going to, I think I can just put this on the same line, hopefully nobody minds. My num trials plus. Okay, does everybody see what that does? So if we have a remainder of 0, let's start with that. Then if the remainder is less than or equal to my rank, and I'm not the manager, I'm going to add something to it. So manager would say, oh yeah, num trials mod size is less than or equal to my rank, but then I am the manager. So because that makes this if statement false, so I'm not going to add my num trials. If the remainder is 1, okay, so I'm process 1, then that's less than or equal to my rank, and I'm not the manager, so I'm going to increase. So I think that works.
But what's the manager here?
What's the manager?
It's not defined in.
I added it up there, so it's under rank and size, it's second to the last.
Okay.
Yeah, I added that in there midway, sorry. But I decided we should do that because.
So can you explain what are we trying to do with this if statement?
What we're trying to do is we're trying to take any extra leftover rows that are not evenly distributed because our size of our number of MPI processes that we're using does not divide evenly into a million. I think we have a million up here. Or is it a billion? I don't even know. Yeah, it's a million. So like, for example, let's say we chose to run this on 7 processes. Okay, 7 doesn't divide evenly into a million. There's going to be some leftover number of that we're going to have to pick up somewhere else, right? So that's what this if statement is doing, is distributing the leftovers It's distributing the leftovers to, processes. So it's just giving one to each of a whole bunch of processes. Okay, makes sense? Yeah.
Just a math question. So the way you have it written now, if I flip that around, it's saying that if the rank is greater than or equal to the remainder.
Oh, did I do that? I
think it's-
certainly did that. Yes, it should be less than. Thank you. Thank you. Thank you. That would have been disastrous, so I appreciate it. Yeah, so the remainder is greater than or equal to the rank. Yes. Thank you. Okay. So then, for everybody, next what they're gonna do is we're gonna come down here and we're going to do my num trials, right? Instead of the num trials in this loop, because this loop is throwing the darts.
The seed, we still want it to be associated with the global I. Here, this I is local I. We want the global I, we want to update I to be related to the rank and this little I.
Okay. So, and then does this belong in the loop or does this belong out?
Below in the loop, the thread seed is local, each MPI or for each this I loop. So
Oh,
the I, you want to replace I with rank plus, replace I with I times the size, then plus rank. So that is the global I. This would assure that the random seed is non-overlapping, non-reproducible for each MPI rank. So it's like the thread seed is scattered way over, and it's independent for each I, for each MPI rank. Otherwise, each MPI rank will use the same seed with this I here. The rank plus parenthesis. We could say, yeah, plus left side parenthesis I times size. But you don't have to parenthesis, just I times size. It's plus I times size. That's it, yeah, parenthesis. Now it's global I.
okay. And then what is this to?
This is okay.
Yeah, that's for long or something, right?
Yeah. Keep it.
Okay, okay.
Now we change.
Okay, but my question is, does this
Sorry,
thread?
the right side parenthesis at L, after L, moved before the last one.
Sorry, what?
Remove the last parenthesis, move it over to after the size.
Oh,
Yeah,
oh, so it should be here.
you should be here, yeah.
Oh, okay.
And then remove last, yeah.
Okay.
That's it.
Okay, but my question for you, Helen, is like, is this gonna reset it to the same number every time when we're going through our number of trials? So should this not be outside of the?
No, we want all the random X and Y to be associated with its MPI rank. But we want to use the global index, global loop index to each MPI rank. Otherwise, the different MPI ranks will use the same seed. My trials is a smaller number than overall trials.
Okay, so. Okay, I'm just trying to. Okay, but then, okay, when we do X and Y, and we send in that thread seed, it's just gonna get the next name. I get it, okay, I understand it.
I need two parentheses there, do we?
No, we don't. I thought at first we were going to, but.
Yeah.
Okay, perfect. I understand it now. It took me a minute, but I got it. Okay, so let me just try to explain this to people a little bit, but I'm not gonna get into huge details. So, there's no such thing as random numbers, really. In programming, what we typically use are pseudo-random numbers, and basically what those are is they are numbers that are generated in a sequence, and they appear to be random. Okay, they're not actually random because they're reproducible. Okay, because of that fact, then there's a whole series of these numbers, right? So what we're doing here is we're picking out certain numbers based on the rank. Yeah, we're basing it, yeah, right. So the seed is what determines how we calculate the number. The seed here is being calculated based on our rank and the particular I guess, index of our loop at that time. So it's gonna pick, like if you could imagine like a whole column of these numbers, it's gonna pick this one, and then it's gonna pick this one, and then it's gonna pick this one. And they're gonna be evenly distributed. And each process is gonna have its own set of those numbers. So that's how this is gonna work. Okay, I'm satisfied.
The compiler is.
What is the difference between the size and that total number of trials? What is size doing?
So size is the size of our MPI communicator, right? So it's how many MPI processes that we are using right now. And so what it's gonna do is it's gonna go, like, let's say I'm rank 0. Let's just make my life easier. I'm rank 0. Size, we have 4 processes. I don't know. And so size is gonna be 4, and then times 2. So it's gonna be 8. So my thread seed is gonna be the base seed plus 8, then plus 16, then plus 32,
Yeah.
then plus, etc. Well, 24, I missed 24, but yes.
I'm confused. It seems like we're using two different conventions here. So when you do X and Y, those have the same random seed,
Yeah.
same thread seed, sorry, but we get 2 distinct random numbers.
We're gonna get 2 distinct random
Because
numbers.
each time you call it, it's a different.
Because it updates itself in the, so let me show you. Let me show you, seed generator. It updates itself here, so so it's gonna update itself.
Yeah, so every time you call it, you get a different sample from that sequence. Which then leads to my question, which is why we have to update the seed within the loop for every pass through the loop, rather than setting the thread seed to the base seed plus the rank, and using that for all samples in that.
We could do it that way. I do think we could do it that way. So I think that we'll try it this way, and then we'll try it that way, and we'll see how it goes.
Rebecca,
Yeah.
you don't need to write and quit. You can do Control-Z and you suspend that job, and FG, you come back.
Of course I can. Thank you. Okay, so we're moving along here. So if x squared plus y squared is less than r squared, then I'm gonna add 1 to my thing, right? To my number in the circle. Right. So then, okay, so this is what everybody is doing, right? And then it's gonna be only the manager, right, who is gonna calculate pi and print out this stuff, right? Everybody agree with me there? Only gonna be the manager. Okay.
What tells it that that's the manager doing that?
Yeah, nothing right now.
Oh, okay.
So we're gonna have to tell it ourselves, right? Yeah.
So this insert variable right here, what scope is this in inside the for loop? Is it in, like, can each process access their own insert
Yeah,
variable?
each process has its own insert. So
Okay.
with MPI, the memory is independent, right? Like for each process. I'm the only one who has access to my memory. When we go to OpenMP this afternoon, it's different, it's shared. But in this case, I always only have access to that because, you're way over there on a different node, right? Compared to where I am. So you can't access my memory. Okay. Yeah, oh yeah, sorry.
Why is it important that we're, like, this section of the code is done by the manager?
Okay, we could choose it to be done by anyone, but if we don't do that, we don't limit it to just one process, then what's gonna happen is we're gonna have all the processes printing this out all at once. If we had 4 processes, we're gonna have 4 copies of this printed out. And it's just gonna be also, because we haven't done any communications yet, it's just gonna be local to them.
But and the code you're talking about is the for loop? Like the for loop is what's gonna be done by
Yeah,
the,
everybody's gonna do the for loop.
everybody's gonna.
But this bottom part here, where we're gonna calculate pi and we're gonna print it out, that has to be done by only the manager, right? Anybody? Okay, so let me just go ahead and do that. So if rank equals manager, and we're gonna do this fun stuff here. We're gonna have to do other fun stuff too, actually, so. Oh, that's. So a fun thing here is we're going to receive counts from other processes, right? That's the first thing we're gonna have to do here. And then we're gonna do all this printing business. Oh, that's exciting. Okay, then if I'm not the manager, then what do I need to do? If I'm not the manager, then I'm gonna send my counts to the manager. Right, so I'm just kind of writing a little skeleton here of the stuff I gotta put in here. Okay, anybody have any questions about that? Does that make sense? So if I'm the manager, I'm gonna receive stuff from everybody else. If I'm not the manager, I'm gonna send my stuff to the manager, right? So the manager is gonna receive the stuff, and then they're gonna calculate pi and print it out. And then we'll be done with our program, right? Okay, so if I'm gonna receive stuff, I'm gonna receive stuff from all of the other processes except for myself, right? I'm not gonna send it myself, that would be dumb. So I probably need, like for loop, right? I need a for loop here, so I'm gonna.
Can I ask about that? Like when you when you call MPI receive, you have to specify the rank you want to receive from?
That's right, yeah. Yeah, now there is a wildcard variable that you could use where you're like, I'll receive from anybody, I don't care. But I didn't teach you all that.
Okay, is there like there's not a single command though that you like, that will like wait until all? I guess that doesn't make sense.
Yes, so there is, and we're gonna learn about that next, because it'll make our lives so much easier. It'll make our lives a million times easier. Okay, so something that we need is a for loop here, so int, I don't know, I don't think we've used J yet. Or int J equals 1, right? Because I'm not receiving from myself, I'm the manager. I'm not receiving from myself, I'm receiving from all the rest of y'all. Int J equals 1, J less than size J plus plus. Okay, so I'm gonna do I'm gonna receive one from you, one from you, one from you, one from you, etc. So I'm gonna do an MPI, oops, receive, and I'm going to receive, oh. Okay, I look at my thing here because I'm gonna cheat here a little bit, but me one, okay, I see. So I'm going to receive into a variable that I haven't defined yet as temp. I call it temp. It's a size 1. It's an MPI long. What are the next things? Yeah, long. Oh, then I need a tag. So let's say J. I'm gonna make everybody send your rank as your tag. And then what comes next after that? MPI com world and status. MPI world status. Okay, and then I'm gonna do circ.
In API receive, you don't have to specify which rank you are, you just have to receive.
No, you just have to specify which rank you're receiving from. And I need to define this temp, but let me just close my loop. Yeah. Define. I'm going to define temp above this. Giggles. So long temp. Right. Does everybody see what I'm doing here? So I'm receiving from you, whatever your count was of your dart throws, I'm receiving that from you. And then I'm going to add that to ncirc. So I'll get the total together in that. And then when I'm done with that, then I'm going to calculate pi. I'm going to compute pi in parallel. Let's call this in parallel instead of serial. And that's how I'm going to get it. Okay. So now if I'm not the manager, right? I am the not the manager, I am the worker. I am going to send, right? Send. So I'm going to MPI send. Okay, and I'm sending you the value that is in ncirc. That's where I collected all mine. It is of length 1. It is an MPI long. I'm going to send you my rank. MPI world. Oh, no, there's no status. No status. Okay.
There's a quick typo to change. At top of the code, MPI status, the S needs to be uppercase.
Oh, okay, thank you.
Oh, it's
Yes,
already, the
right here.
lowercase right now.
Yeah, it needs to be uppercase, yes.
Okay.
Thank you. Thank you for finding that.
It's MPI underscore uppercase status.
Mm-hmm.
Okay, see. You know how to toggle upper and lowercase?
Mm-hmm.
Just do that.
Tilde, yeah. It's my favorite trick.
Yes. And Am I understanding correct that the MPI receive will be waiting for the number one finish and then send it?
Yeah,
and then-
yeah,
Okay.
yeah, it will, it will. Yeah,
Are we gonna have a, I forget the term, like is it gonna be trying to receive and not getting anything because the receive is like, how do we know that the non-manager processes are going to send and on time for receiver,
Okay.
manager receive?
yeah, so I mean, if they took forever, then we're just gonna have to wait forever, that's life. But in our code here, okay, what's gonna happen is, let's say I'm a non-manager, okay? So the way I'm gonna view this code is I'm gonna come here, I'm gonna figure out how many trials I get. And then, maybe I have to get one extra or whatever. I'm gonna do all of my, dart throws, okay? I'm gonna calculate my end circ, and then I'm gonna come here and it says, if you're the manager, and I say, well, I'm not the manager. So then I'm just skip all that stuff. Right, and I'm gonna go to this else, which means I'm not the manager, and then I'm gonna send. So there's not gonna be any like deadlock, except for anything intrinsic in sending. But there's not gonna be any deadlock because I'm never receiving. Like I ignore that part where it says, if you're the manager, receive, because I'm not the manager. I'm just like, I don't care about that. I'm doing the part that's my job. Yeah.
But the manager is going to loop through like the other processes one by one, right? And try to receive from each consecutively.
Mhm.
Doesn't that require that all of the other processes send before the manager tries to receive?
They don't have to send before the manager tries to receive. It's just the manager won't move on until they do send. So this is, okay. You can write any code that you want just about using these 6 basic MPI commands, but that doesn't mean that it's efficient. So this is really inefficient, right? Because yeah, if processor 3, has a million other things to do, doesn't get to you in time, then you're going to be waiting there on processor 3, and you're not going to receive from processor 4 until you're done with 3. So yeah, that would be inefficient. And so like I said elsewhere, there is like a wild card that you could put in for who you're receiving from if you wanted to. And then it would just be a matter of and there's also a wild card for the tag also. So you could, if you could trust it, you could just trust that you're gonna receive size -1, receives from anyone, whoever gets there first gets there first. You could do that. Yeah,
The manager is calculating itself. It's throwing darts as well, right?
so.
The manager is throwing darts.
Yeah.
Is it reading itself?
Yeah, it's throwing darts. It's just adding everyone else to its sum was in NSERC, so then it's
Okay.
just adding
Okay,
to
got
that.
it.
Yeah, yes.
If we had run this and we benchmarked it, and we saw that the communication from one process took the same time as calculating 10,000 throws, for example. Could we assign sort of a triangular distribution of the number of trials for each processor to compute so that the manager does smallest number and then it's ready, and then the next one
Yeah.
communicates, and the next one is still computing, and then it communicates, and
You could certainly do
balance the
that.
time
Yeah,
between them.
definitely do that. If you had, so I mean, these dart throws are trivial, right? But if you had, instead of throwing darts, if you were doing something that was actually hard, then yeah, you could definitely do something like that. You could also use some kind of well, we're gonna learn a little bit more in OpenMP when we get to that about sort of different work chunking sort of ideas. So you could chunk the work. But yeah, in this case, I can money back guarantee that they're all going to take the same amount of time and we don't have to worry about anything like that. But if you did, there are other techniques that you could use for sure. Okay. All right. So shall we see if my code compiles? This is going to be the challenge of the day. If I can get it in a single trial here, we'll see. So I'm using the C compiler, which is CC. darts.c. Oh, wait a minute. I actually want to move this. Okay. Move darts. C, I want to call it darts dash MPI. Let's see. That's really what I want. Okay. So then I'm going to CC darts dash MPI dot C minus O darts dash MPI. Okay. So the minus O thing means I want it, instead of just being called a.out, which is the default, it's going to call my program, my executable darts dash MPI. Okay. So let's see, cross our fingers. Oh no! Oh no, too few arguments too. Okay, what am I? Okay, I missed an argument somewhere. So let me go back and look. Disappointing. Usually I can. I'm gonna blame the fact that I was on vacation. Okay, so here is my problem. Too few arguments to MPI receive. So here's what I had. I had temp, one, MPI long, J, MPI commonwealth, and status. So what it wants buffer, that's temp. Count, that's one. Data type, the source. The source and the tag, yeah. Okay, so I need J comma J, and then, okay. So, okay. Let's blame that, yeah. Okay, so then, okay, here similarly, I didn't put the destination. Okay,
The tag will search for a message from that source with that tag.
right.
Okay.
Yeah.
Okay, so that's my mistake, okay. I was just too excited about vacation. Darts.
That complete,
Okay, so silly me, forgot those things. So I need to put the actual source here, so oh. Yeah. Okay, there, and then I need to put in here, I need to put manager. And rank, then it'd be the combo. Okay. All right, so just so you know, when you get those scary error messages like that, they are actually telling you what's wrong. It's just you could look at it and be like, you know. And I'm really glad we're not using templated C++. As
Control Z.
Okay, it doesn't matter. Okay, I'm gonna do this again. We'll see how I go. Oh no!
Or wasn't this my comment at the beginning?
This was your comment at the beginning, yeah. Okay,
12 minutes.
okay, we'll do that. We'll just copy that bad boy in there. I didn't think it mattered. So I confess to being wrong. That's my one mistake for the day. Okay. ArgC, ArgV.
Hold on a second, please.
Okay, I'm just writing it.
Okay. Okay.
Okay. Going to do that. Oh, it worked. Woo! All right, come in.
The previous command, you just copy the file where it was and you just renamed it darts MPI.
Yeah, I just renamed it.
Okay.
Yeah.
And then,
Can you bring back the main line?
So, yeah.
Oh. Wrong space. Extra space.
Okay. So, I at least successfully compiled it. It doesn't mean that it's actually gonna work, but at least the compiler could compile it into something sensible.
You declare the temp variable somewhere?
Sorry.
The temp variable somewhere?
Yes, I do. I declared it in the if I'm the manager right here. Okay. Yeah,
What's the command to compile again?
it's lowercase c, and then the thing that you're gonna compile. And then minus O, the name of what you want it to be called. Okay, so I'm gonna try to run this thing. So in order to do that, I need to get onto a node. Right, in our case, we have this beautiful reservation. And I'm gonna get myself a CPU. Okay, so I'm gonna use this command right here. And I'm gonna get me my node here.
Oh, I got it.
There we go. There we go.
So in the minus N is asking for one node.
One
and the
node.
minus C is asking for 16.
Yeah, we're
Yes.
sharing a node.
Yeah, 16 cores out of the one node, and the minus Q shared means I'm willing to share my node with you, with other people. I own like half of a node right now. Basically. Okay, so I want to try to run my job. So remember I have, let's see, I have my Dart.MPI here. It is an executable, that's what this X means. Sorry, this is my own little abbreviation, but it's LS minus L type head to show me just like the top most recent files in this directory. So the most recent one here is this Dart MPI. And that's my executable, and it says RWX, meaning read, write, execute. Those are my permissions on this file. I can read, write, and execute this file. So that's good news. So I'm gonna try it. srun minus n, lowercase n, 1. And I'm gonna do Dart-MPI. Let's see how we go. Okay, everybody cross your fingers. Cross your fingers. Oh, look at that.
Oh, it's one.
Okay, it was just with one, right? So it wasn't in parallel. It's just with one,
One is good.
but it worked. That's pretty good. Okay, so now let me try it actually in parallel. So I'm going to try it with 2. See how it goes. Oh, what?
And train as it is.
Oh,
See, what was mine?
Yeah.
you on, you have the entry.
I don't know. That would be like our RSV pile.
Yeah. You got it. I got it.
So that's not gonna be email. Okay, that'll be it.
So we just paste in that command then?
Yeah, although it doesn't want me to do more than
তো দিলে যাবো।
Yeah, it's probably.
minus C. Gotta do minus C.
Yeah.
H.
Probably in the is alloc.
Yeah, that works. Okay.
Can we time it? Like, is there like a command to like,
Oh, to time it?
yeah.
Yeah, sure. I mean, you could do time, srun, blah, blah, blah. Yeah, I mean, this is like such a short program, but you could change it to be 1 billion instead of 1 million, and it would take a lot longer, and then you have some meaningful timings in that case. Okay, so in order to run it, oh, I didn't do the right thing. Yeah. So if I wanted to, run it like this, then I've got to change this minus C value here. So this is great, and we get the same answer every time. Terrific. Thank you, Helen. Yeah,
Sorry, what are the S run minus N and minus C doing?
excellent question. So the minus N tells it how many MPI processes. Minus C tells it how many like cores, cores that it needs to use for each MPI process. Yeah. So because my salloc command was, let me find it, was minus C16, then basically the minus C and the minus N arguments multiplied together has to be less than or equal to 16.
Oh.
Makes sense? So if I do 8, then I gotta put this down to 2. Awesome. All right, and I can do 16. That's probably all I can do. And go higher on half of a node. Okay.
In terms of computation, should these all run like with roughly the same time, even if you scale up?
Yeah, I mean, they're going to, because this is such a small calculation, but like if I change it to 1 billion,
Yeah.
then you will see a difference.
Between each of these.
Between each of these, yeah. But ultimately in these, because the parallel overhead is so large compared to the actual computations that we're doing.
Okay.
Yeah.
And so when setting like number of processes and cores, is that like on a per project basis that we need to like figure out if we want to be as efficient as possible?
Yeah, you would probably want to run a few like little scaling studies with different sizes and figure out which one you get the best bang for your buck.
Okay, I see.
I scaled to 1 billion and I got the same runtime.
Oh,
Need to like.
maybe we need to scale to 1 trillion or something. I don't know. I don't know.
Okay.
Hmm.
But the darts.mpi, if I recompile that with 1 billion,
Yeah, you'd have to
that solution definitely works.
recompile it and in order to get the billion. I mean, we could rewrite it so that we can put on the command line how many darts we want to throw. Rewrite it that way, and then we wouldn't have to recompile it for every number, but